U-substitutions is an integration technique that allows us to look at an indefinite integral to see if it actually integrates back to a composite function. Now, when we are looking at indefinite integrals, we always want to first analyze it to see if it's one of our very beginning type of indefinite integrals where the integrand can be rewritten to apply our basic integral rules. But if it's not one of those, then we want to look further to see if maybe it's a u-substitution, or later on other techniques like integration by parts or trig substitution, different things like that. But if it's not where it goes back to your basic indefinite integrals, the u-substitution is the next thing you look for. Now, I have linked in the description of this video other videos that I have on indefinite integrals, and actually another one of u-substitutions of different indefinite integrals than these. So if you need a review of your basic indefinite integrals, make sure to click on the video and watch that first. And then if you have watched this and you want to see other examples of u-substitutions, click on that link as well. Here we're going to look at these three examples to start with. Now, this first one, the integral of sine to the ninth of x cosine x dx. Remember, we don't have an indefinite integral rule that allows us to go backwards on a general product of two functions. It doesn't exist. There's kind of a little bit of a hybrid sort of a thing with the integration by parts, but just straight going backwards on a product of two functions is not a thing. Now, there are a couple trig functions that actually were, when you differentiated them, a product of two trig functions, and they go back automatically. For example, the derivative of secant x with respect to x is secant x tangent x. So if I'm integrating secant x tangent x dx, that just goes back to secant x plus c. So that I don't look at as a u-sub because it is the indefinite integral integrand is the derivative directly back to a trig function. That's not the case for this one though. In this one I have sine to the ninth of x times cosine x dx. And so really remembering that the 9 power tucked in with a trig function means that that sine of x is to the power 9, and then I have my cosine x dx. This one has an action on a variable expression, and this variable expression's derivative is not 1. So when that occurs, you want to try to see if maybe it is something that we could get a better look at it by using a u-substitution. With the u-substitution, you're going to have a workspace over on the side. And on the workspace, we're going to assign u, and that's just the variable that's been decided that is commonly used, to be the expression that's being acted on. So this power of 9 action is on this sine of x. So I'm going to let u represent sine of x. And then over here, I'm trying to see what its differential would represent. So do the differential du, and remember the differential du will equal f prime of x dx. So du is equal to, well, the derivative of sine x is cosine x, and then the differential dx. Now, once you've gotten this figured off to the side, you come back to your original question and you see if everything replaces back into the variable u. Okay? So here I have my u is representing sine of x, so I'll put a u here. So I have the integral of u to the power 9. And this cosine x times dx, that entire expression is needed to be replaced by the differential du. So all of this cosine x dx goes out and we replace it with its equal du. Now everything's been transitioned over to u's and du's, and it's one of those types of expressions that we know how to integrate. The indefinite integral of letter base to number power, as long as the exponent's not -1, is keep the letter base, add 1 to the exponent, and divide by that. And multiplying by 1/10 is the same as dividing by 10, and then plus c. Now I just want to go back to the original variable that we started with. So we go back and we look at what our u was assigned to represent and put it back in our expression. So I have 1/10 times the quantity sine x to the power 10 plus c. And then remember that we have a more simplified notation for this. This would be 1/10 sine to the power 10 of x and then plus c. So that is our indefinite integral of answer to this problem. Let's look at the next one. Here I have the integral of 5x times this 2x plus 8 to the 18th power dx. Now, if I had a problem that had a power of, say, 2 up there, I would probably square out that 2x plus 8, so multiply that all out and then multiply by the 5x through and integrate it term by term. We rewrote integrals that were like that in a previous video. But the power 18 is way beyond what I'm willing to multiply out in order to have the benefit of integrating it term by term. So what we want to do is try to see, well, is this new u-substitution thing going to help out at all? We are going to let u represent the expression that's being acted on. So this power of 18 is acting on the 2x plus 8. So u is going to represent 2x plus 8. Now, when I do the differential du is equal to f prime of x dx. So du is just equal to 2 dx. And when I look back, I'll put my u where the 2x plus 8 is, but I just have the dx here that matches. I don't have the numerical factor of 2, as well as there's an x still there, and I can't leave an x in the expression when I transition over to the u's. This problem, however, is going to have something that we will be able to do to compensate for that. See, I can't pull letter factors out in front of the integral that match the differential. However, in this u assignment, u is equal to 2x plus 8, it's actually something that I could very readily find out what the u expression is that is the same as the variable x. Just solving this for getting the x on a side by itself. And I only need to do that, again, because that letter x was still there after I made the substitution. We are going to bring this down here and say that if my u is equal to 2x plus 8, what if I want to get the x on a side by itself? Well, I'd have to subtract an 8 from both sides. U minus 8 is equal to 2x. And then divide both sides by 2. X is equal to 1/2 of u minus 8. So that's the expression I'll be able to put where the x is. Also, this is a numerical factor of 5. This has a numerical factor of 2. Number factors I can actually divide to the other side so that my replacements are easier to see. So if there's no 2 factor individually, so I'm going to divide that factor of 2 over to the other side and see that 1/2 du is going to be the replacement for dx. Now sometimes people say, well, if you put the factor of 2 in here that wasn't there before, you can put a 1/2 out in front because 1/2 times 2 is 1 and it doesn't change the value of the integral. Either way you do it is exactly going to be a correct process to lead you to the answer. All right, so now let's make our replacements. So this is going to be the integral. I have my 5. Instead of x, I'm going to put in 1/2 times the quantity u minus 8, because that's what x represents. And then next, 2x plus 8, I'm going to put in u, a power of 18, and then dx has to go out and a 1/2 du goes in its place. So now when I look at that expression, I see these number factors that aren't in the parentheses. I can take those number factors out in front of the integral. So 5 times 1/2 times 1/2 is 5/4. So this will be 5/4 times the integral u minus 8 times u to the power 18 du. So I just took this 1/2 times this 1/2 times this 5 out front. Number factors you can bring out in front of the integral. Now we're almost ready. I don't have an integration process for a product of two functions, but now this parentheses just is to the first power. It's not to a higher power. So I can go ahead and just distribute this u to the 18th to each term. So I have 5/4 times the integral u to the 19 minus 8 u to the 18 du. This gets me to the point where now I can apply my indefinite integral rules. Remember, with plus or minus, we integrate term by term. Letter base to number power, as long as the number power is not -1, we add 1 to the exponent and divide by that. So I'm going to have my 5/4 times 19 plus 1 is 20, so I have u to the 20, and then divide by 20 is like multiplying by 1 over 20. Then minus, I've got the 8, and then I'm going to have u to the 19, and then I'm going to divide by 19. So I have 8/19, u to the 19, and then plus c. Next up, we're going to distribute that 5/4 through. So 5/4 times 1 over 20 is 5 over 80, u to the 20, minus 5/4 times 8 over 19. There will be a common factor of 4 top and bottom that'll remove. So that'll actually end up being a 10 in the numerator and a 19 in the denominator. U to the 19, and then plus c. And then lastly, we're going to take out the u and look back at our good notes that we wrote out to see what we were doing. And we're going to take out the u and put in the 2x plus 8. So I have 5 over 80 times the quantity 2x plus 8 to the 20 power minus 10 over 19 times 2x plus 8 to the 19th power, and then plus c. So that one did have that trickier component to it, and we only had to do that because when we looked at what our substitutions were doing, we still had a variable x that wasn't involved in the substitutions right at the beginning, and we had a way from what we let u represent to find out what x is equal to in an expression in u's and still complete the process. This next one is the integral of the cosine of 3x dx. Now cosine is acting on 3x, and the derivative of 3x is 3, not 1. So even if it's an action on an expression as simple as 3x, a u substitution is what you can use in order to make sure that you get the correct indefinite integral answer. So cosine's acting on 3x, we're going to let u represent what's being acted on. So we have u is equal to 3x. Then look at the differential. Du is equal to, well, the derivative of 3x is 3, but it's the differential, so 3 dx. So du is equal to 3 dx. Now if I make my replacement there, I'll have cosine u, but this is dx and that's 3 dx. A number factor that's not matching with your original integrand, you can divide to the other side. So I have 1/3 du is what the replacement is for dx. So now with our integral, we have the integral of cosine of u, and then take out the dx, 1/3 du goes in its place. And that's just multiplication, so if it gets confusing that it's in there, just factor it out in front of the integral. So I have 1/3 times the integral of the cosine of u du. The integral of cosine u du is sine u, and then plus c. So I have 1/3 sine u plus c, and then take out the u and replace it back with what you let it take the place of. So this is 1/3 sine of 3x, and then plus c. Here's 3 more examples where u-substitution helps us to integrate the expression that we have. Now, this next one is the integral of 2x minus 4 times e to the x squared minus 4x plus 3 dx. Again, I don't have anything that lets me integrate a product of 2 functions in general, so I'm going to see if this is something that might help be able to go backwards on with a u-substitution. The action of, like, the input is the exponent on that base of e. So let's let u equal that x squared minus 4x plus 3. Then think of what your differential is. The differential du is 2x minus 4 dx. And then look back and see if you have that as a replacement exactly or a constant multiple of that. So with my u being replaced here, and then I do have the 2x minus 4 exactly and the dx. So this goes back exactly. Now, it could be a constant multiple, in which case we would just have to work with it a little bit more. Like this could have been 10x minus 20 or something like that, and we still would have been able to work with our expression to use our u-substitution. But here it's directly back. This is the integral. It's e to the, take out the x squared minus 4x plus 3 and put in the u there. And this factor 2x minus 4 as well as this dx, these 2 factors together, they have to go out to put in the equivalent du. So then I look at this, I'm like, well, I know how to integrate e to the u du. That's e to the u plus c. And now that it's integrated, I just need to go back to the variables that we originally used. So take out the u and put the x squared minus 4x plus 3 back in. So it's e to the x squared minus 4x plus 3 plus c as the answer to that indefinite integral. This next one's subtle, and sometimes when they're subtle, they're a little bit harder to think about. So let's go through this one as well. So here I have the integral of e to the negative x dx. See, the integral of e to the x dx goes back to e to the x plus c. But the expression sitting up in this exponent, this negative x, that derivative is -1, not +1. So let's go through the u-substitution and see what happens. If u is replacing the negative x, then look at the differential. Du is going to be -1 dx. And I don't have negative dx, I have dx in there. So we're going to divide both sides by -1, and negative du is what we replace the dx with. So now when we look at this integral, this is the integral of e to the u, and when you take out the dx, its replacement is negative du. And put that in parentheses so you don't mistake it as a subtraction. And this factor of -1 that's assumed when we have that negative du, we can bring that out in front of the integral. So that's negative the integral e to the u du. Now it matches with our basic integral with our exponential function e to the power. So the integral of e to the u du goes back to e to the u, and I have a minus in front, so negative e to the u, and then plus c, and then take out the u and put the negative x in its spot. So be very careful on those. And then this final one, we have this integral of 4x minus 2 over x squared minus x plus 4 dx. We don't have an integration process for the division of two functions in general. So I need to make a u-substitution, and I also want to remember that when I'm looking at the differential, I'm taking the derivative. So the action actually here is this expression, x squared minus x plus 4, got thrown in the denominator of a fraction. So we are going to let our u be the representation for x squared minus x plus 4. du is 2x minus 1 dx. And here's where my u is going to be, and my numerator here is the expression 4x minus 2 dx. And this is 2x minus 1 dx. It's not the same, but it's only off by a constant multiple. So actually I can see up here there is a common factor of 2 that we can factor out of this expression in the numerator. So I can write this as the integral of 2 times 2x minus 1 over the x squared minus x plus 4 dx. And I didn't do anything that wasn't there. If I did something new that wasn't there, I would have to compensate for it. But this expression had a common factor, and all I did was factor it out. This factor of 2, this number factor, I can bring in front of my integral. Then the 2x minus 1 dx together go out, and a du goes in its place. And you can either put it in the numerator of the fraction, or you can put it off to the side. And I'm going to put it off to the side here with a 1 in the numerator. And then my denominator is x squared minus x plus 4, what I let u represent. So here we're integrating 2 times the integral of u to the negative 1 du. Now, letter-based to number power, as long as the number power is not negative 1, I would add 1 to the exponent and divide by that. But this power is negative 1. And if I add 1 to negative 1, I get 0, and I can't divide by 0. That's your cue that you can't do that, add 1 to the exponent and divide by that on this particular expression. This is the one that goes back to the natural log of the absolute value. So here I have 2 times the natural log of the absolute value of u plus c, and then go back to your expression in x's. So it's 2 times the natural log of the absolute value of x squared minus x plus 4, and then after that plus c. So I hope these examples have helped you get a little bit more strength in the idea with the u-substitution. There's a lot of different problems out there that u-substitution helps with. This is just an introductory video for this topic, and I'll be posting some more soon.